All right, let's resume today's discussion. We are going to wrap up the stationary distribution in Markov chain, and after that, we are going to talk about the random walks on graph, specifically undirected graph. We are going to start with the stationary distribution, and then we are going to move to the commute time, and finally, we are going to talk about the cover time. And if we have time, we are going to move to chapter 8. That's going to be our continuous random variables. Right. So let's get ourselves started. Let's wrap up the Markov chain part. Right. So recall that in Markov chain we have a transition probability. Right. The probability is defined over the set of states times the set of states. Basically, Pij is really just the probability in the next step. I'm going to be j in conditional in the past step. I was in I. Right. So the stationary distribution, despite that we mentioned a lot of properties at the end, the stationary distribution is really just that one stable point associated with the transition probability. That is the pi equal to pi times t, right? Where pi is a stationary distribution. Right. Right. So basically, last lecture says that like if p behaves pretty well, like for instance, is ergodic, then there's exists one and then a periodic, then there exists one unique stationary distribution. Right. So today we are going to just talk one more property associated with the stationary distribution, and then we are going to move forward. Right. That's theorem 7.10, and consider the, finite, irreducible, and ergodic Markov chain, right, with transition probability p, then if x6 and pi, so I don't know, like I'm not sure whether that's a stationary distribution, but it has this kind of property, such that sum of everything is going to be one. That makes sure that this is a stationary, this is a distribution, and for any ij, we do have this property pi ij equal to pi j pij, right? Right. So this is also the definition of the time reversible. Right. So in case like in the future, like you wonder what is the time reversible Markov chain, then basically whatever stationary distribution that also satisfies this property, then it's called a time reversible Markov chain. But at this moment, what we need to do is that we say that in case we are able to find a subject pi that satisfies this relationship, then pi tilde is going to be a stationary distribution. Right. So the way we are going to prove that is we really just need to verify that verify that pi equals to pi p. Right. This is all we need to do. So now let's really just pull out one particular column out of that, right? So if I look at the j's column, right? Right? So this is really just the p1j, p2j, and so on and so forth, pnj, right? And if I use this j's column and multiply this whole vector pi tilde here, we will get if this were true, then we will be able to get pi tilde j, right? So this is how the matrix multiplication is done, right? So we just really need to verify that. Let me write down need here to make sure that this is our goal. We haven't proved that yet, right? But this whole thing is pretty straightforward, right? So if I just multiply this pi with this column, this is what I'm writing here: I equal to 0 to m pi I, pij equal to pi equal to summation of I equal to 0 to n, right? Let's use the equation here, right? So tilde pi I times pij actually equals to tilde pi j times pji, right? And then there's one common term here, then I can pull this out, right? So this is pi j tilde, right? And summation of I equal to 1 to n pji. So, and this part basically sums to 1. This is really just by the definition. Right? So, at the end of the day, this is pi j. So, That's a pretty straightforward. That's a pretty straightforward thing. So let's really just make one additional remark. Why this is equal to 1? Let's really just write this down by pji, right? So basically that means that the interpretation is that if I start with the j state, I sum up all possible outgoing states. What's the probability, right? So by the law of total probability, this is 1, right? So this is one additional remark, right? So after that, then we're going to move to the random walk on graph. Random walk on graph. Right. So let's start with an arbitrary graph. Say that this is, let's say the A. Let me just draw something. Right. So so things like that. Right. So this will be just a graph I'm making up arbitrarily. Right. So that it could be edges like this. C, D, E, F, G. Right. So it's, in general, it's a directed graph. So for instance, look at A and C. There are actually two edges moving from A to that there are actually two edges. One is moving from A to C. The other one is moving from C to A. Right. So our definition of of random walk on this kind of graph is pretty straightforward, right? So it's basically we start with a fixed position. This position can either sample from a certain distribution, or really you just say that I want to start with D, right? And then I look at all the outgoing edges, right? There are 3 outgoing edges, right? So then what I'm going to do is really just to decide to travel one of the outgoing edges with the same probabilities, right? So basically with probability a third, I decided to move to G, and the probability a third, I decided to move to E, and so on and so forth. Right. So let's say that I decided to move to B, right? Right. So now this is my second stage, right? So this is the walk one equal to D, and then the second stage equal to B, right? And I'm going to do the same thing, right? So here, like, it's a bit funny that this B doesn't have any outgoing edges. Let me just draw things like that, right? And draw things like that, right? So now B has 2 outgoing edges. Right. So again, we can do the same thing, like with probability half, I'm going to move to G, and with probability half, I'm going to move to E. Right. So then I can just keep doing this kind of things and walk, right? So basically, in other words, it's really just the probability my next stage equal to V, condition on my last stage equal to U is really equal to 2 possibility is 1 over degree of U if UV is an edge, 0 otherwise. Right. So 1 over degree is really just means that whenever I'm going to move to the next stage, I'm counting the number of edges I'm connecting to. Right. Each edge have uniform chance to be traveled true. Right, so that's the reason it's 1 over degree. But in case when we are not connected, then basically the probability is 0. Right. So this whole thing can be done again for this is the directed graph, right? So this version is directed, right? And the whole thing can be done by can be defined under the undirected graph again, undirected graph. Right. Undirected graph really just means that the edges doesn't have directions, right? So let's say this is my undirected graph, right? When edge doesn't have directions, no direction, right? That also implies that you can traverse through either direction. Right? What does that mean? That really just means that like when there's a direction of the edge, you really just think that this is a one-way road. And then when there's no direction, that really just means that the traffic, you don't have any constraint on the direction of the traffic, right? So now, when you do a random walk, it's the same definition, right? So say that I start with A, then there are 3 edges that I'm connecting to, right? Then the probability I'm traveling across one of these edges is are the same. They are equally 3. Right, say that with probability a third, I decided to travel to B, and then I indeed did that, right? So now there's another things, right, going on, right? So now B is connected to the A, C, D, E, right? So again, that with 1/4 of the probability, I'm going to travel to one of these edges, right? So just notice that, right? So because this is undirected, right? So A moves to B, that really just implies that there's an edge connecting between A and B. And when I'm at B, there's actually nothing prevents me moving back to A, right? So it's completely legitimate to have a path that's the random walk that's A move to B, move to A, move to B again, and so on and so forth. Right? Although this probability is not going to be very high, right? So this is the random walk on the undirected graph, right? So now let's start with the first result here, right? So so the first result here is really just the lemma 7.12, right? This one is that something that we are not going to prove, and then but that's something that you can just look at the textbook because it's pretty straightforward. So a random walk on an undirected graph G is a periodic if and only if G is not bipartite. So basically that really just says that like the only thing that's making the random walk on graph is periodic is that this is bipartite graph. Bipartite graph means that you can really split the nodes into two sides so that the edges are all crossing the two sides. There aren't any edges that looks like that. There aren't any edges that are connecting nodes on the same side. Right. So this is a lemma I think you should need to be aware of, but it's not a very difficult one. At least I don't find that too much insightful. Right. So let's start with the real major one that we need to prove, the theorem for 7.13. Right. So a random. So it's really just talking about a stationary distribution. On graph G, on undirected graph. So it says that a random walk on G has a stationary distribution pi v equal to degree of v divided by 2e. So what does that mean? That really just means that if I look at any random walk, right, on this graph, right, so this is my random walk. And I want to be able to pull out the stationary distribution. This is pi, this is A, B, C, D, E, F. Right? So I want to sort of write out my stationary distribution pi A, B, C, D, E, F. Right? So the denominator is the same for everyone. And then it really just says that in the stationary distribution, the mass associated with a particular node is really proportional to the degree, right? So now our degree here, let's really just count the degree of every node, right? So we have 3 edges here, right? So degree here is 3, and then we have 1, 2, 3, 4 edges here. The degree here is 4, degree here is 2, degree here is 3, and degree here is 2, right? And degree here is 2. Right? So I can sort of write this down in this way. Right? So A is 3, B is 4, C is 2, D is 3, E is 2, F is 2. Right? So it needs to divide it by some constant, right? So constant. This constant is really just the 2 times the number of edges, right? So the number of edges here is 1, 2, 3, 4, 5, 6, 7, 8, right? So divided by 8. But from time to time, this constant doesn't really matter too much, right? So if I really don't know the constant here, let's say it's divided by the same C here, right? So I just really need to make sure that the sum of the pi I equal to 1 is really just the 3 plus 4 plus 2 plus 3 plus 2 plus 2 divided by C is going to be 1, right? So then I can figure out this C here. I believe it's 16. It's not 8 because it's 2 times E, right? So it's 16. So in other words, in any ways, right? So what's really important is really just the stationary distribution is proportional to the degree. Right? So here I want to make 2 remarks here. 2 remarks. The first one would be what would be related to the regular graph D. Right. So it's what people call degree regular graph, right? Degree regular graph says that if I have graph, it's undirected, and if I'm not sure whether I can draw everything, right? So if I look at the degree of every node here, right? So So the degree of every node here has the same degree, right? So if dg of u is the same for all u in the edge set, then we are really just say that this graph is C regular graph. Right. Now let's consider a random walk on this C regular graph. Right. So basically, if we do the random walk on this C regular graph, we really just if we just compute the stationary distribution, we really just have that the stationary distribution are really proportional to the degree times 2e, but the degree is the same. That really just says that the pi u is going to be the same for all u. That also means that the distribution, the stationary distribution, is uniform. It's uniform. Right. That basically means the distribution looks like that: 1 over n, 1 over n, and so on and so forth. So it's 1 over n. Right. This is the first remark. Right. In the second remark, it's sort of related to page rank. Right. I'm not sure how many of you are familiar with the Google's original ranking algorithm for the web pages, right? So I think around 20 years ago, Google came up with this idea saying that, well, if I want to do search, I want to search whether like, I want to search for buying cars like BMW. So I want to make sure that I want to check that like which website is the most authentic website that's selling BMW, right? So so before Google, like what people were doing is that like we just look at the text associated with each of the website, right? It says that, well, maybe this website says something relating BMW, and then you also says something related to car, right? So then there's a good chance this website is relevant to the search here, right? And maybe this another website says a little bit of BMW as well, and maybe it doesn't say car, it says other things. Then just look at the content. You believe the somehow the whatever algorithm probably just believes that, well, because it doesn't mention car, maybe it's less relevant, right? Google has come up with this idea that the importance of a web page, it really depends on how people talk about, depends on how other people talks about you. Right. So what does that mean? That means that if I am a website, right? I'm maintaining my own personal website. I provide a link to this website, and then someone says that this is selling BMW. And also imagine that people just somehow believe that I'm a professor in the Will and Mary. I'm probably honest, and then the fact that I'm providing a link probably saying that this website has some credentials, right? So it's believable, it's trustable website, right? It's really just because that maybe like people just believe that I'm a trustable person. Right? So they somehow generalize this idea, right? Come up with that graph. Come up with a graph, right? So basically that represents the links to each other, right? So the link basically says that there's a website A, website B. If there's a link connecting from A to B, that basically means that there's a website that's here, like there's some link here that helps me to click. When I click, it directly helps me to jump to B, right? So Google's page rank idea is really just one of the first ideas that ranks the web pages. Right. So when the way it does is really just that, let's really just perform a random walk on this graph. Right? Perform a random walk. And then I come up with a stationary distribution for each node, right? So let's say this is 0.01, this is 0.02, this is 0.3, right? So stationary distribution really just intuitively means that if I walk that long enough, what's the portion of the time I'm visiting this node? And Google's idea is that in case in the stationary distribution, you have one particular website has a larger density, that basically means that the website could be more important, right? So this is actually one of very important algorithm that's really helping us to rank the importance of different websites in a directed graph. And people, right, of course, like the random walk here, like it's not really just direct or simple random walk. It makes some a little bit minor tweaks. If you're interested in that, you can look into the very old paper. But this idea is really just that if you perform a random walk on directed graph, then look at the stationary distribution, and there's a good chance that you can learn the importance of each node on the graph, right? And then later, people suddenly realize that, well, I can sort of use this algorithm to rank anything so long as the set of items you are interested in really have some graph represent interpretation. There's a graph connecting one item from another item, so long as the graph is directed, right? So for instance, you can talk about ranking the importance of different cities, right? So each node could be a city, and an edge here is really just that the amount of cars or traffic that's moving from one city to another on an average day, right? So then you can sort of rank the importance of city. Then people even like it's getting a bit hackish. Like people sometimes get even one step further. It says that let's even run page rank on an undirected graph, right? So or this kind of undirected graph. It says that let me also try to figure out that can I get the importance of each node in an undirected graph, right? But when you start to get into this kind of idea, is really just get into too hackish, right? So because as we sort of learned just now that if you just look at the stationary distribution of undirected graph, you don't need to even run the random walk. You just need to count the number of the degree of each node. The higher the degree is, the heavier the mass there is in the stationary distribution, right? You don't really need to run any random walk, right? So this is very different from the setting where we were facing the directed graph, and the stationary distribution cannot always be explicitly characterized by the in degree and out degree of each node. Right? So here is the second thing. Yeah, this is the second thing I want to mention, that when you look into page rank and you want to apply page rank to graph, you need to be very careful. Like in the undirected graph, you're not supposed to run page rank. Okay. Now let's move to the next part. I'm talking about the cover time. Let's talk about the cover time. Before we talk about the cover time, let's recall what is the commute time. So commute time, HUV, is really just the expected number of time to visit V for the first time if we start at U. Right. So let's really just use a picture to illustrate that, right? So I have a graph, and I start with U. Let's say this is U, and let's say this is V, right? So I start with a random walk. I count the amount of time I need in order to visit U, and this would be HUV. This is expectation, right? So really just recall that. Let's recall that like there's a relationship between the stationary distribution and the commute time. Right. So basically, pi I is really just the 1 over HII. Right, so this is what we are going to need next, right? This is also discussed in last lecture, right? So now let's look at the next lemma we are interested in. Lemma 7.14. If U V in E, then let's look at the commute time HUV plus HVU. This is going to be bounded by 2 times of E, right? 2 times the number of edges. Right. So let's see how this can be. So there are actually 2 ideas associated with this proving this lemma. So what do we really need to prove, right? So let's say there's an edge connecting between U and V, right? So again, like we are really assuming this is an undirected graph. The book didn't make this clear, right? But a lot of results that are written in this section are really just related to undirected graph. Some of them are incorrect for directed graph, right? So let's look at, like, it's a large graph. There are a lot of edges, right? So let's really just look at two nodes that are connected by a pair of edges. Right. So we really want to compute the given bound of edge UV plus edge VU. Right. So that effectively is really just that if I start from V, I do a random walk. How long is it going to take for me to hit U and then walk again and hit V again? Right. So this is really just that I start with a random walk starting from V to U and then another random walk that goes to V. Right. So now the expected time it's counting here is really just that the first idea is it says that like I don't count in this way. What I really want to count is that let me just draw everything again. If I really just count a random walk, right? Let me start with here, right? This is U, this is V, there's an edge here. If I count a random walk, that walks a long way. That goes through U and hit this edge and come to V again. Like how long is it going to take? Right. So I count another random walk. That start with U, that walks a long way. That start with V, sorry. Walks a long way and go to U and directly use an edge between U and V and come back to V. Right. So this is actually a tighter version of the typical random walk that's defining the HUV plus HVU, right? So I have a stricter requirement of the type of random walk I'm looking for. And so basically that's only one possible way of moving from V to U and back to V, right? So that basically means that the expected time of here is going to be at least as large as the expected time of the HUV plus HVU. And then we are going to give an upper bound here, right? So the second idea here is really just that we can view the Markov chain as an equivalent chain on the edges. Right. What does that mean? Right. So let me just start with a simpler one. Right. So let me just say that like this is my Markov chain, right? A B C D E. Right. I can talk about random walk, like so when I have a random walk of A to B, B to C, C to D, right? I can have random walk that's on the nodes, right? So this is usually how we describe the random walk, right? So A move to B, B move to C, C move to D, right? So and so on and so forth, right? But we can also equivalently represent the same random walk as the edges, right? So I can say that well, A move to B, right, and then B move to C, and C move to D, and so on and so forth, right? So to use the edge to encode the information of the random walk, right? So basically that means that each edge here, right, each edge here is really associated with it's mapped into two states. The first state would be like it's really just that one state it's moving from one direction to another, right? The other state would be just the other direction. Right. So we are really just converting each of the edges into two states. Right. So now, so what let me just repeat. What we are doing is really just that so instead of viewing the graph as a collection of states on the nodes, it can also be equally viewed as a collection of states on the edges, and the edges can even direct it, right? So the edge states. Now, if I just draw everything here, right? So this, let me just use this node to represent BA, and then another node to represent AB, right? So and let me also think about this one. This is the AE, and there's another node called EA. Right, so basically for each of the edge, right, so the edge here, right, so the edge BA is mapped to BA, AB is mapped to AB, and then EA is mapped to here, right, EA is mapped to here, and AE mapped to here, right? So each direction of the edges is mapped to a new state here, right? So this is what I call the equivalent Markov chain. Then we can also define the state. Like for instance, if I move from B to A, and then so which state I'm going to move to next, right? So in this one, there's only one state I'm going to move next, that I have to move to E, right? There's only one state, right? So so now I can also use the edge to encode this piece of information. If the last stage is B to A, right? So let's say this is the B to A mapped to the last stage here, right? And the next thing, the next edge I can move to is only A to E, right? So I make that edge here. So in case, let's also add one more edge to make this problem a bit non-trivial. Let's say that there's another edge connecting between A and D, right? So then starting from A, I can actually move to three places. I can move to D, I can move to A, I can move to E, right? So A has three places, like AB, right? So and AD and AE. So, and just now actually I forgot, right? So if this is the red one is actually the not only one I can move to, right? I can also move back to the AB, right? And now because I added this edges, finally let's just at the last minute I add one more edges, right? So there will be I need to look for another node that's encoding AD, right? So and then I also allow me to move here, right? So again, the movement probability is uniform. Does that make sense? Right. So now, so basically, really just that a graph that with the node state, that is presented by the node state, can be converted into a graph. This is a directed graph, right? And then that's represented by the edge state. So each one is each node, each state here is represent directed graph, directed edge. So now, just now, we were interested in a particular edge connecting between U and V, right? So here, then that corresponds to two nodes, right? So there's one called U to V, and then there could be another one called V to U, but we don't really care, V to U. Right. So now, how do we? So now let's go look back to what we were looking for. We were looking for a random walk that move from V to U and directly use the edge of U to V. Right. So basically, we were looking for, let's say also draw something here, right? So let's say this is U and this is V, right? There's an edge here. We're looking for a random walk. Let me just delete this, change a different color. We were looking for a random walk that moves from V to U, U to V. So let's really imagine we want to, so let's do a mathematical exercise. It's really just we start with V, we just keep waiting until the first time we hit U and hit V again, right? So in order and I count the total amount of time I need to wait until this happens, right? So what the textbook says that, now I need to look for a starting point V, right? So let me just repeat, I need to look for a starting point V. And then I just wait until I hit U and I hit V, and then I count the whole time, and that's it. Right? The textbook says that now. So instead of directly starting with V, let me just wait. Let's really just you imagine there's something that's working here on the node state, and correspondingly the same thing is working on the edge state. There's two things happen at the same time. So I'm not starting. I don't directly start with putting the active state to directly be on V. I just keep waiting. I wait in the second graph until the first time I hit the state UV. Until the first time I hit the state UV, hit this state. Basically, that means that until the first time I walk through this edge UV, then. Basically, that really means that this is the edge state, right? So that really means that at this point, if I look back to the vertex state, then basically the node state, then I'm at this point. This is at T. This is at T, right? And up to this point, then I start to being the counting, right? So I saw the node that it maps to V, right? I do the counting, and I count the amount of time I need in order to hit UV again. count the amount of time again to hit. That really just means that in the node state graph is hit U and hit V. Right. So now if I look at the second graph, it's really just from UV to UV, right? It's really just from UV to UV, right? It's really I look at I use the state that are in the edge state. It's really just I'm looking at the expected hitting time from UV to UV. Right. So this is, as I said, is in the stationary distribution is pi UV. Right. This is what we did the last time. It's really just the reciprocal of the pi UV. Right. 1 over pi UV. 1 over pi UV means what? Means that if I look at the graph that consists of the edge states, what's the stationary distribution for the node of pi UV? And it turns out that if you do the math carefully, this if I look at, so this is the conclusion, right? So conclusion for I'm making up a claim, and you need to verify this claim on your own, and then it's pretty straightforward math, right? The conclusion is that if I take a walk on this on the graph consists of edge states, the stationary distribution, it's uniform, right? The state, so just look at the state. There's a little bit conceptual subtleties here, right? So when I talk about the stationary distribution, it's on the set of states here. The set of states here are really just the set of the directed graph edges, right? So this is quite different from what's happening here when we are looking at the node states. The stationary distribution are on the nodes, and the stationary distribution here are on the directed edges, right? So and the number of state in the edge graph here is really just that the 2 times number of edges, right? So because the each edge is converted into two states, because there are 2 directions, right? So that really just means that 2e is really just that it's gives information about pi UV. More specifically, pi UV is actually 1 over 2e, right? If you look at this 2 equation, right, you can sort of imply HUV is going to be 2e. Right? HUV means that if I start with this state, I travel again, and then what's the expected time for me to hit back the state? It's going to be 2e. Right? But again, like if you look at the way I'm counting, right? So I have to do a bit of waiting until in the second graph I hit through this of a specific edge, and then I start counting u. But on the other hand, this Markov chain is memoryless, right? So regardless where do I come from, like I'm specifically interested, I come from U to V. But regardless where do I come from, the next time I really hit the same, I hit the UV again. It's really just that doesn't depend on the history, right? Even I count things in this way, it's the same as counting things in the first way in which we directly start with V. So that really means that this piece of expected time is the same as the expected time we are looking for. It's the same as the expected time we are looking for. And just now we were showing that this expected time is going to be 2e, right? And that's the reason that at the end of the day, right? So what we are doing here is that this one is going to be less than equal to 2e. And then it's an upper bound of the sum of the HUV plus sum of HVU. This is lemma 4.14, 7.14. Right. So now let's move to the next lemma, lemma 7.15, the cover time of a graph.